Good
Good
morning,
morning.
Professor.
Good to see you. Pleasure to meet you.
What a thrill. What an honor. How are you?
Very good. The honor is mine. My goodness. You certainly have a long history of basically deep and perceptive commentary to make.
Well, thank you. And like you, I was there early on the internet just after you were. Uh, I was on a Usenet group in the very early 80s and discovered how toxic spam was. And I got my first email address in 1976. So I have you to thank for all of that.
You know, I remember back then, I'd be doing research with my students in my office. And then one day I walked into their laboratory, a bullpen of students, and they were all doing work that didn't look like they were doing research. I said, what the heck are you doing? And they were deep into news groups,
Yeah.
the underground movement of photography and, magic and such.
Yeah. Yeah. So I want to talk about so many things. We don't have a lot of time, so I'm just going to dive in. I hope that's okay.
Sure.
Start us off, if you don't mind, with a layperson's understanding of what Plan 55 was at Western Union and how that has anything to do with the fact that you and I are thousands of miles apart and talking to each other.
You've done your homework. Very good. That was a rather advanced telegraph system for sending information from one site to another using relatively high-speed lines with switches at the ends of those lines. But when a message came in from one end of the switch, they had to carry it across by tape, punch tape.
Like a piece of paper.
Piece of paper, and feed it into a receiver at the other side of the room and forward it. And that was the way they implemented what we call store and forward. You receive something, you store it, and then you forward it to the next node.
All right, so I'm going to slow you down for a minute because I understand engineering a little bit because I faked it in college, but a telegram, for those of you who have never gotten one, piece of paper with some typewriting on it that somebody would run up to your house and hand to you. And my expectation of telegrams was there was a wire from the person who was busy typing in the Morse code all the way to the place where they printed it. But obviously that doesn't work when you got a lot of places. So you need to have a hub and spoke, right?
A network where things go hop from node to node, if you will, from hub to hub, if you will.
And there was a human being who was going to take this piece of paper and walk a few steps and put it into a new machine.
That's right.
Okay.
And the tape would fall on the floor, long rolls of it. And they wondered which piece of the hub should I plug it into? And it said on the tape, next goes to Chicago. From Chicago, it goes to Denver. And it was done manually. And the big innovation in those days was to make a wire between the various inputs and outputs in that hub to make it happen automatically.
Right.
Very clumsy and very specific. It was for telegrams only.
Right. And why is there a queue? Where does the queue come in?
Well, the queue in that case is if multiple messages came in at one side of the node, all going out on Chicago, if two came in at the same time, one had to wait. So the operator would hold one, feed it in, and then the next one. Or it would be, as I said, paper tape on the floor.
And so you thought deeply about what the priorities would be in queuing theory, because it's everywhere, queuing theory, but most people don't even see it. I did a podcast about it a couple of weeks ago.
Interesting. So if we back up a second, the idea was to allow more sophisticated devices to communicate, not humans writing telegrams, but things called computers, which were emerging in the late 50s, and find a way for them to communicate. So the idea would be, why not use the telephone network? That was a wired network.
Yep.
It was very effective for voice, very good for voice. Turns out that data coming out of computers is very different from voice traffic for a very important reason. When you and I talk on a telephone line, there's a continuous wire from me to you while we're talking. And if I decide to have a cup of coffee while we're talking, or pause, those wires are wasted.
Yep.
It turns out with speech, you're silent about 1/3 of the time, which is okay. In data, you're silent 99.99% of the time. The lines are almost never used, and these data lines are expensive.
Right.
So you couldn't use the telephone network. So we needed something like a store and forward network instead of a continuous connection, where, as you said, a message comes in and it goes hop, hop, hop across this interesting network. And along the way, you're going to get congestion. There'll be many messages trying to go out in the same line. What do? You put it in a queue. What do you do with the queue? Well, a few things. You can serve it first come, first serve. You can serve it by priority if somebody pays more. But importantly, a queue is a very wonderful device that shares resources efficiently. A queue, a server in a bakery store at a queue, will not wait for a customer who's not there. There's somebody at the counter, they're going to get served. In the telephone network, the server was idle waiting for you to finish your cup of coffee.
Right.
While you're doing that, someone else can come in and get served. So queuing theory was an adaptive device which dynamically shared the expensive resources. And you could prioritize things if you wanted. But queuing theory, the mathematics, allows you to study exactly what you want for a networking environment. For example, you study how long the waiting times are, what the throughput is, what the efficiency is, what the buffer size is, all those things a network designer needs to know. So queuing theory was exactly the right tool to use to design and analyze these systems.
But I'm guessing that there were skeptics and that you had to spend a fair amount of time. It wasn't just like, Eureka, I discovered this. There were probably a large number of people who said this will never work, or came up with 100 reasons why it wasn't the right solution. Did you hear a lot of that?
Oh, all the time. Initially, the reason I studied this problem at MIT, because nobody else was looking at it. Nobody else cared about it. It was a new problem which would have impact if you could solve it. And I had an approach. So I studied it. I basically laid down a mathematical theory of the way these networks should work and be designed. Then I went to AT&T, the biggest network in the world, and said, look, you guys, build a data network. And they said, it'll never work.
Right.
And even if it does work, we want nothing to do with it.
And just to insert a little irony here, AT&T, of course, the progenitor of AT&T was Alexander Graham Bell, and they brought the telephone to Western Union, the people who made telegrams, and Western Union said, we're not interested, and even if it works, we want nothing to do with the telephone. So history repeats itself. So you show up and you've got this. How hard was it to even explain packets and this whole idea of discontinuous queues when people were used to hearing about it being the other thing?
Well, the telephone industry was well versed in queuing theory. The guy who started the telephone network stuff was a guy named Erlang. He created queuing theory. So they understood the mathematics behind it, but they didn't see the need, the demand, or the business reason. And they were right. They were making a lot of money on voice network. Nobody was sending data. Why build a network? How foolish, how short-sighted. But the point you make, I find very interesting. First, the Western Union, the telegraph network, the type we're talking about, refused the telephone network. And now
Exactly.
I love it. I'd never thought about that.
Okay, so now let's talk about ARPA for a minute. My uncle, who's a genius, also from MIT, told me about ARPA for the first time when I was 13, so 1973. But you were in there before then. And what, the phone just rang one day and they said, it's the Pentagon. Are you available? How did that happen?
No. It started with Sputnik.
Right.
1957, the Russians launched Sputnik. They caught the United States with our pants down. Eisenhower said, this will never happen again. So within 3 months, he created the Advanced Research Projects Agency, ARPA, to do what? To bring back the capability of America in STEM, science, technology, engineering, and math. So it would be number one again. So brilliantly, he created this funding agency, which would support research across all those domains in the United States at universities, at industrial research labs, et cetera. And these labs, these research groups began to develop some wonderful technology. And they'd go to a new researcher and they say, look, we know you're good. Here's a pile of money. Go do something great. You can keep the money for a long time. We're not going to bother you. Failure's okay, just keep going, but shoot for the moon. Now, as a commenter, what a wonderful funding philosophy. What more could a researcher ask, and what more could motivate someone to do great stuff? So they did that, and a number of great centers arose. And each time they went to a new researcher would say, hey, buy me a computer. ARPA said, sure, I'll buy you a computer. And the researcher would say, gee, I see that the University of Utah has really good graphics capability. I want that. And University of Illinois has high performance computer. I want that. And ARPA said to these investigators, we can't give everybody everything, but if you were in a network, you want to do graphics, you log on to the University of Utah through the network and use the facility there. So the idea of the network was to share resources. It's not that they wanted a network. They wanted to make more efficient use of the funding.
Right.
And so they said, we need a network. Aha, how should we do it? Now, it turns out they enlisted one of my classmates at MIT, a guy named Larry Roberts, to be chief scientist. And he knew all about my work. In fact, we worked together on a number of things. He brought me in to help specify it. And that's the phone call, if you will.
Right.
Specify it, write a spec, send it out to industry, get them to build the physical switch, and off we go. And they decided that UCLA, where I was now a faculty member, would be the first node on the network because I had the expertise. I knew how to test this network. I knew how it should behave. And so we became the network measurement center of this fledgling network. It was our job to break it, stress it, push it to its outer limits.
Right.
And we could.
The legend is that the very first email was ever sent was sent from your office, and it was only 2 letters long. Is that close to true?
Close, not total, because it wasn't an email. There was no
Okay.
email. It was a message.
Right.
And what we did is, from my laboratory, we decided when we had one node, we couldn't test this network. One node
Right,
is
it's not a network if it has one node.
exactly. So when we had 2 nodes in October of 1969, we said, let's test the capability of this network to do just what I said before, to sit at one node, log on through the network to a second node, and get in and start using their facility. So all we had to do was log in from UCLA to Stanford Research Institute, the second node, which is 350 miles to the north. And all we had to do was log in. Now, to log in, you type LOG, and that remote machine will type the IN for you. It knows what you're doing. So here we go. Had a programmer down at my lab, a programmer up at Stanford Research. And to make sure this was working, we had a telephone connection between them. Yes, you see the irony.
Of course. You could have sent a telegram, but that would have been slower.
That's for sure. But we're going to develop a technology that's going to eat the lunch of the telephone network, because eventually did replace it. So my programmer, Charlie, typed the L. Said, you get the L? Bill said, yep, got the L. Type the O. You get the O? Yep, got the O. Type the G, you get the G. Crash. So the first message ever was low, as in lo and behold. I added that later.
All right, so I want to shift gears now that we've laid the groundwork, because most of what I am focused on is culture and how we bend the culture and how we change the culture. So ARPA had a very specific culture. So did the tech world. So did UCLA. I was on the internet when the rules were still really clear. There were no .com sites because businesses weren't welcome. And everyone wants to know if you got your razor back.
Very good. You've done your homework.
So again, the legend probably told by you is that you left a razor at a conference and sent somebody an email saying, can you please send it back, which is against the rules because it was for personal use, not because it was part of the system. I like exploring this feeling of which rules do we need to honor and celebrate because they are who we are, they are our culture, and which rules are simply there to keep us from speaking up about making it better. And my hunch is that you've spent a career balancing between those two.
Yes, but you've characterized the issue that so many people miss when they look into the history of the internet. I referred to a little bit before the way DARPA had this wonderful funding culture. Now let's take that one step further. Who received that money? Principal investigators, faculty. What do you do with that? You fund your graduate students. How do you do it? The same way. You go to a graduate student, you say, look, we have the following problem. Go solve it. Use your brain, organize yourself. We'll give you plenty of money. Shoot for the moon. Failure is okay. So that environment was a golden era of creativity, of innovation, of organization, of culture. And that culture was just, here we were nerds solving some problems. Money was not an issue in terms of patenting and forming startups and all the rest. We didn't want to own this technology. We wanted to create it. So we nerds were having a great time. And that, referring to allowing people in, that culture persisted for quite a while. And when National Science Foundation came in the 80s, they beefed up the backbone network, and they were in charge of who could join. Initially, it was just computer scientists. When the National Science Foundation came in, they allowed all forms of science, biologists, chemists, physicists, and they had to adopt a policy, what they call an acceptable use policy for who could access the network. And there comes culture again. They had a very liberal, simplified, acceptable use policy. And they didn't restrict almost anyone. They said, come, we want people, because getting back to your first question, initially we couldn't get anybody to join the network, never mind AT&T. The computer scientists didn't want to join. Nobody could use it. It was very complicated until it got a little more mature. So we wanted to encourage use. And the same with NSF. And sure enough, it began to expand. And it was in the late 80s when some of the people being supported would say a chemist. Where does a chemist work? In either university or chemical laboratory, a research laboratory in a chemical company.
Right.
So what goes on? These guys, what are they doing? What are these chemists doing? They're using email. That was the main application.
It was the killer app. Yeah.
Absolutely. And nobody anticipated it, by the way. It was a surprise. So these guys are using email, and the managers are looking, the executives looking, the staff are looking, gee, that's pretty nice. I'd like some too. So it left the laboratory into the commercial side of the company. And that's when the dot-coms began to appear.
Right. So we had Bolt, Baranek, and Newman. I remember they were there early. And we had people who were MCI Mail tried to build an email network on top of the whole thing, right? And they couldn't, their strategy was to get CEOs to use it. CEOs had no interest whatsoever in getting a hold of it. So again, we're back to this cultural problem of, you used to be able to send an email to somebody and their secretary would print it out and walk into their office and hand it to them, right back to paper tape, right? And so you're constantly leaning against what's normal. And one of, we're gonna share this on a modern network like Instagram, where normal is now something totally different than what normal was for me 30 years ago or for you 50 years ago. And I guess as I try to put this into a nice bow here, what's your instinct about how the culture is going to shift now that Metcalfe's law has reached infinity, right? Now that everyone is on the network, what do we do with it? What would you like to see happen with that thing you helped birth 80 years ago or 60 years ago, whenever it was?
So there's a few things. That's a wonderful open question. First thing is my initial thinking as to what the network would become has in many ways happened. I predicted it would be always on. This is back before the network began. Always on, always available. Anybody with any device could get on any time. And it would be invisible in the sense that it wasn't an ugly thing to fuss with. Well, all of those things happened except the invisibility, which is part of the answer to your question.
Yeah.
But what did I miss in that prediction? I missed exactly what you spoke about before. I missed the social network side. It wasn't about computers talking to each other. It was about people talking to each other.
Yeah.
That was a surprise. Email demonstrated that. So along the way into the 80s and then finally the 90s, in the 90s, some very significant things happened. The web came in. We had a strong backbone network. We had the .com saying we want capability. What was missing was a good user interface, which is called the World Wide Web.
Right.
And then it reached the consumer and the commercial world. And when that happened, a major shift occurred. We shifted from doing high technology, advanced networking, nerds, to a world where we became a supermarket, an entertainment channel, a gossip channel, social network, and it began to talk about money instead of technology.
Right.
Major shift occurred. So at the same time, the devices became more complex. People are playing with keyboards. Executives didn't type in the past. Now they all spend their time typing. That was a secretarial task to be delegated. So my notion of this invisibility is that we should return to a case where we can use the network the way you and I are right now. We're speaking with each other, we're gesturing, we're touching, you watch my face, I understand your speech and your view. The network should disappear into the infrastructure. And that's happening now with Internet of Things.
Yep.
It's embedded in our walls, in our fingertips, in our automobiles, everywhere. And so it's disappearing into the infrastructure just the way electricity, which was my example way back then. Electricity is a terrific capability. It's 2 holes in the wall. You plug in, you get electricity. No big deal. You don't have to type a URL address or anything else.
Yep.
The network I should be able to talk to a network when I walk into a room. It should be everywhere. And it's starting to behave that way with Internet of Things, with the advanced wireless technologies, et cetera, and the artificial intelligence, deciding what I should learn and what I could hear. So that's going to happen. And when that happens, I predict we're going to have what I like to call a basically pervasive global nervous system.
Yep.
Called the internet right now, where you'll be able to, when I walk into a room, it knows I'm there. I walk up to a device, it takes on my personality and my privileges and my preferences and my profile, et cetera. So I see it moving into that nirvana, if you will. But along the way, look where we are. The dark side of the internet has bubbled up dramatically. Initially, it was just a nuisance. People send you spam, and irritate you. No longer the case. It's no longer a teenage playing. It's now becoming an adult with really nasty behavior.
Yeah. I don't think it's the dark side of the internet. I think it's the dark side of humanity. And, what I missed in all of my prognostication about the web starting in the 80s is I just assumed that people would rise to the occasion, that anonymity would fade away, and that people would see this tool and make things better. And I just forgot to keep track of trolls and short-term profit maximizing capitalists. And when those two groups get together, the culture gets disrupted. And so I'm no longer a techno-utopist, but I am hopeful that more access, deeper for more people, the arc of it bends toward dignity and not toward hatred.
That's a beautiful goal, certainly. And I hope we achieve it. But we've gone almost beyond the money side of it and the profit motive, which has been so basically demolishing of the network. We've got nation states now. We saw it just the other day. And those are serious players. They cause enormous harm to our infrastructure, to our economy, et cetera. And I fear that what's beginning to happen is nations are beginning to put boundaries around their network.
Yep.
And we're getting what we like to call a balkanization, separate networks, which won't talk to each other. And once that happens, you lose the enormous power of the internet, which is open access everywhere, free, trusted, open, anonymous, et cetera. So that's a very serious issue, which we have yet to deal with. I love the idea, I love the goal, and I love the fact that it really is a human problem. But we need technology solutions to help us get through this bump in the road, and it's a big bump in the road right now.
So on that, Doctor, I'm going to wrap this up. I want to say, as someone whose life could not have been more transformed by your insights, thank you. And I hope that your optimism is well-founded, because we're all in this together now, because we're all on the network. So thank you for your time, and thank you for making magic.
My pleasure. Thank you very much. Pleasure talking with you.